Hi everyone, my name is Paulo and I will present the paper Chemistry-Inspired Pattern Formation with Robotic Swarms. This work is inspired by self-organized emergent patterns that can be widely seen in particle iteration, producing complex structure, such as chemical elements and molecules, and by revisiting some concepts and theories, applying particle iteration and molecular structure formation, we create a minimalist model suitable for robot swarm control. The main contribution of this work is a novel stochastic and decentralized approach that allows a swarm of heterogeneous robots to emerge with interesting patterns, relying entirely on local information. Moreover, we believe that this approach has potential use in various scenarios, especially those where we want to build more complex structure from simple ones. A possible application is modular robotics, in which complex robots are built from simple models and can dynamically change their shape. Another application is the construction of temporary structure, such as bridge and platforms with different industry and military uses. So now let me explain how our methodology works. Initially, let us assume a swarm composed of heterogeneous robots moving in a bounded environment, and we want to find appropriate velocity commands for each robot. The first step here consists of modeling the configuration of the swarm as a dynamic Gibbs Random Field. This basically describes the probability of the entire swarm being in this configuration, but the classical approach assumes global knowledge. And in this paper, we show how we reduce this model in order to reach this probability function here that assumes only local information. So basically, given this probability function, each robot sample velocities in a decentralized way, using only local information, leading the entire swarm to reach the minimal global potential. However, there are still some key aspects in this work that will drive the swarm to a certain behavior. This is defined by the combination of potential functions, and here to reach group formation, cohesive navigation, and obstacle avoidance, we combine the Coulomb-Buchner potential with the kinetic energy. The Coulomb-Buchner potential defines how a pair of robots should interact, attractively or repulsively, and the kinetic energy induces alignment in the velocity of the robots of the same group. Another key aspect is the definition of neighborhood system. In this work, we use atom perpetuals such as mass, electrical charge as a swarm heterogeneity factor, and the octet rule of chemistry to define the neighborhood system. So basically, using simple binding rules between two atoms, we could select the robot's neighborhood to form different patterns depending on these rules. And eventually, if we keep the robot sample velocities commands in this probability function, it will converge on the patterns, and these patterns are dynamically moving from the environment. So now let me explain and let me show you some experiments to make it clear. Here we have two simple examples of swarm composed of hydrogen and oxygen that produce a structure that resembles water molecules. And we also have hydrogen and carbons producing structure similar to methane. Here we have two more complex shape formation examples. The first one assumes a swarm composed of hydrogen, nitrogen, and carbon, produces structures similar to polyamines. And we also have oxygen and carbon producing oxocarbons. After showing the diversity of patterns formed by our method, we select this chain-like oxocarbon structure as an interesting candidate for case study because of its directionality. So as a case study, we show through physical simulation and real robot experiments the application of the method to dynamically form shapes with a topology similar to a bridge. In this carbon-like, in addition to the carbon-like and oxygen-like robots, we define these anchor robots to delimit the ends of the structure. allowing us to control the structure using human swarm interaction. So basically, we wait until the chain is formed, and then we started operating these anchor robots in order to interact with the structure. We also performed these experiments using real robots as a proof of concept. And we also, but we change, we do not use these anchor robots, we use this black box here. And we start moving after the bridge is totally formed. So to sum up, this paper presents a novel decentralized approach that allows a swarm of heterogeneous worms to form different patterns and shapes in an emergent fashion. Experiments using numeric simulation demonstrate the versatility of our approach in producing different patterns by setting only the bound constraints. Moreover, we also present physical simulation and real-world experiments in which a swarm was capable of building chain-like structure, which is potentially attractive for more tangible applications. Thank you.